Hello everyone. In this video, we see the second part of the solutions of ordinary differential equations and their properties. So here we see the previous year solution in PG level related to ordinary differential equation. So here we see basic to higher idea of linear ODE and their solution properties. Basic to higher idea of linear system of ODE and their solution properties, and the questions and solutions related to national level exam. So question number 1 is, if the solution phi 1 phi 2 up to phi n of the homogeneous vector differential equation dx by dt equal to at into x be the fundamental set of solutions of the system, and phi be an arbitrary solution of the system, then phi can be expressed as a linear combination of phi 1 phi 2 up to phi n. Okay, so before proving this theorem or to find the solution of this equation, at first we see the definition of the fundamental solution or fundamental matrix. So consider the homogeneous vector differential equation dx by dt equal to at into x, in which x is an n by 1 column vector. Okay, so a set of a linearly independent solution of this system is called fundamental solutions of the system, and the matrix whose individual column is a fundamental set of solutions is called fundamental matrix. That is, if phi 1 phi 2 phi n be fundamental set of solution, then M considered as a fundamental matrix which is given by this M. Okay, now we move to the proof of the theorem. Let us consider phi 1 equal to the column matrix phi 1 1 phi 2 1 up to phi n 1, then phi 2 equal to phi 1 2 phi 2 2 up to phi n 2, and phi n equal to phi 1 n phi 2 n up to phi n n. Okay, and consider the initial condition phi t0 equal to u0, where t0 belongs to closed interval AB and u0 equal to u10 u20 and up to un0 is a constant vector. Okay, now consider the linear algebraic system c1 phi 1 1 plus c2 phi 1 2 plus cn phi 1 n equal to u10, and last equation is c1 phi n1 plus c2 phi n2 plus dot 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 up to cn phi n equal to un0, where n equation we get n equation with n unknowns. Okay, so since phi 1 phi 2 phi n is a fundamental solution of the homogeneous differential equation, therefore they are linearly independent on AB. That means their Wronskian not equal to 0. Okay, so now if we consider this Wronskian at a particular time initial value, that means t0, so which is the coefficient determinant of the above system? If you consider the variable c1 c2 cn, then the coefficient determinant given by w phi 1 phi 2 phi n. Okay, so automatically, because we consider phi 1 phi 2 phi n are linearly independent, therefore Wronskian not equal to 0. That means at the particular value t0, the Wronskian also not equal to 0. That means this system has unique solution c1 c2 cn, because coefficient determinant not equal to 0, and we know the property of linear algebra. When the system of equation non-homogeneous system of equation has unique solution if the coefficient determinant not equal to 0. That means we know that x equal to a inverse b, where determinant not equal to 0, proves A inverse exists. So in the same way, here we consider the coefficient determinant not equal to 0, that means the system has unique solution. Therefore, there exists a unique uh, solution of this system of equation, and for C1 C2 C1 we can write the linear combination C1 phi 1 plus C2 phi 2 up to Cn phi n equal to U0. Therefore, phi T0 equal to U0, and here we consider U0 equal to summation Ck phi k. So if we define a vector psi t equal to Ck phi k t, where psi t is a solution of 1. Next section we prove that psi t is how this phi t is a solution of the system. Okay. And when we consider t equal to t0, then it is clear from the above equation psi t0 equal to phi t0. Okay. Now, since phi it is a solution of the system, therefore we can directly write d phi I by dt equal to at phi I for I equal to 1 to n. Okay. So differentiating psi with respect to t and using the linearity property, we see that C1 d psi dt equal to C1 d phi by dt plus C2 d phi by dt up to Cn d phi n by dt. Okay, up to n terms. So using the property d phi dt equal to a phi, we get the second line. Then taking common at, we get C1 at into C1 phi 1 plus C2 phi 2 plus dot 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 plus Cn phi n, and this combination also we already considered as psi t. Okay, therefore d psi dt equal to a psi t. That means the solution psi also satisfies the differential equation d psi dt equal to at psi t. So psi is also a solution. So here we get phi t, psi t both satisfy the same initial condition or initial value problem dx by dt equal to at into x. So here x t0 equal to phi t0. So by uniqueness theorem, for linear system of differential equation, the solution of this initial value problem is unique. Therefore, phi t equal to psi t. That means the phi can be expressed as linear combination of phi 1, phi 2, dot 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 phi n. Okay. Okay. So next, move to the next question. The question is, let phi 0 be any solution of the non-homogeneous linear vector differential equation dx by dt equal to at into x plus ft, and phi 1, phi 2, dot 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 phi n be fundamental solutions of the corresponding homogeneous differential equation dx by dt equal to at into x. Then prove that number 1, the vector function psi equal to phi 0 plus summation k equal to 1 to n ck phi k is also solution of the non-homogeneous system. And number 2, an arbitrary solution phi of the non-homogeneous system is of the form phi equal to phi 0 plus summation k equal to 1 to n ck phi k. Okay. So how can we think? At first, we filtered the main question. Okay, we have to prove that psi equal to phi 0 plus summation k equal to 1 to n ck phi k is a solution to the non-homogeneous equation. Okay. Oh, given that phi 0 is a solution of the non-homogeneous system, therefore phi 0 satisfies the equation. That means d phi 0 by dt equal to a phi 0 plus ft. Also, phi 1, phi 2, phi n be fundamental solution of the corresponding homogeneous differential equation. That means each phi k also satisfy the homogeneous system of equation. That means d phi k by dt equal to at phi k. Okay, so substituting this psi into the left hand side of the non-homogeneous, differential equation. We get d psi dt equal to d phi 0 plus summation ck d phi k dt using the linearity property of differential operator. Okay. So substituting the results d phi 0 dt and d phi k dt into the above equation, we get d psi dt equal to at phi 0 plus ft plus summation ck at phi k. So now taking common at, we get at into phi 0 plus summation ck phi k equal to ft. Therefore, d psi dt equal to at psi plus ft. That means psi t is a solution of the system. Now we prove the second part. That means each phi can be expressed as phi 0 plus summation ck phi k. Okay, that means phi be an arbitrary solution satisfy the non-homogeneous system. That means d phi dt equal to at phi plus ft. Now defining a new vector function u as a difference between this arbitrary solution and the non-homogeneous solution phi 0 u equal to phi minus phi 0. So differentiating this u with respect to t, we get du dt equal to d phi dt minus d phi 0 by dt. So substituting this into the non-homogeneous equation, we get du dt equal to 85 plus ft minus 85 0 plus ft. So after calculation, we get 80 into u. That means u satisfies the homogeneous equation. That means du by dt equal to 80u. Now, since phi 1, phi 2, phi n form the fundamental solution of the homogeneous differential equation, so any homogeneous solution you can be expressed as a linear combination of them, because we already proved the theorem n is the phi 1, if phi 1, phi 2, phi n be fundamental solution, then any function phi can be expressed as their linear combination. Okay, so that means you can be written as u equal to summation ck phi k. Okay, so u equal to, we already consider that u equal to phi minus phi 0, so phi equal to phi 0 plus u. So substituting this value to the above term u equal to ck phi k, we get phi equal to phi 0 plus summation ck phi k. So this completes the proof. Okay, thank you.